For almost 20 years, one number ruled this topic: 66 billion solar masses, the biggest black hole ever measured, big enough to swallow our entire solar system 40 times over and still have room left. Every video on TON 618 opens with that number like it's carved in stone. It's not. A different measurement method cut that mass almost in half. And in 2025, astronomers found a completely different black hole, weighed with a completely different method that might actually be a cleaner measurement than TON 618 ever got. So which number do you trust? That's not a trick question. Astronomers are asking it too. And the answer says more about how we measure the universe than it does about TON 618 itself. Let's get into it.
Quick reset, because you need this before the real story lands. 1957, a routine sky survey. Astronomers scanning for faint blue stars log an object as entry number 618. Nobody blinks. It looks like a star. Case closed. It wasn't. In 1970, a closer look at its light showed something impossible for a star. The light was stretched, redshifted, way beyond anything a nearby object could produce. That stretch is a distance marker, and the distance it pointed to was billions of light years away. Something that far away, still bright enough to trip a survey built for nearby stars? That's not a star. That's a quasar. Quasi-stellar radio source. Looks like a star, isn't one. Here's what's actually happening. A black hole sits at the center of a distant galaxy. Gas and dust spiral toward it, forming a flattened disk. As that material gets dragged inward, it accelerates. Friction between particles heats the disk to millions of degrees.
At that temperature, the disk doesn't just glow, it floods out radiation across the entire spectrum. X-rays, ultraviolet, visible light. Enough light to outshine every star in the galaxy around it combined. That's the mechanism. That part, everyone agrees on. TON 618 sits at a projected distance of roughly 18.2 billion light-years, but the light hitting our telescopes right now left it about 10.8 billion years ago, when the universe was only 3 billion years old. We are not looking at TON 618. We're looking at a photograph of it, mailed to us over 10 billion years ago, and it's just now arriving. Nobody disputes any of that. The fight starts the second you ask one question. How much does the thing in the middle actually weigh? That's where it gets messy.
You can't put a black hole on a scale, so astronomers use a workaround. Gas near the black hole orbits at a speed set by how strong its gravity is. Faster orbits, heavier black hole. Astronomers read that speed off the width of a specific emission line in the quasar spectrum. Sounds solid. Here's the catch. There isn't one line to pick. There are several, and they don't all agree. In 2004, one team measured the hydrogen beta line and got 66 billion solar masses. That number became the standard. Every documentary, every summary, every video since has quoted it. In 2019, a different team ran the numbers using a different line, carbon-4, which sits closer to the black hole and behaves differently. Their answer? 40.7 billion solar masses. Read that gap again. Not a rounding error, a 40% swing. Nobody made a mistake here. Both teams used accepted science. They just picked different rulers, and the rulers disagreed. So if someone asks you right now how big TON 618 actually is, the honest answer isn't a number. It's a range, somewhere between 40.7 and 66 billion solar masses. Most sources still quote 66 billion, not because it's more accurate, but because it got there first and stuck.
Either number still makes TON 618 one of the heaviest black holes ever measured. That's not in question. What is in question? How confident should we really be calling anything the biggest when our own measuring tools can disagree by 25 billion suns? Sit with that for a second. That's not a footnote. That's the whole story. For almost 2 decades, TON 618 didn't have real competition. Phoenix A star got floated as possibly bigger, up to 100 billion solar masses, but the measurement was too shaky for anyone to take seriously. TON 618 kept the crown by default. Then 2025 happened. A different team used a completely different technique, not spectral lines, gravitational lensing. Here's the idea. A massive object sitting between us and a distant galaxy bends the light passing behind it, like a lens. Measure exactly how much that light bends, and you can calculate the mass directly from gravity. No emission lines, no guessing how gas behaves near a black hole, just geometry. Using this method on a system called the cosmic horseshoe, astronomers measured a black hole at roughly 36 billion solar masses. Lower than either TON 618 number. But that's not the point. Lensing measurements are considered more reliable. Fewer assumptions, no dependence on which emission line you happen to choose.
So here's the uncomfortable question. If a lensing measurement lands at 36 billion, and our 2 best guesses for TON 618 disagree with each other by 25 billion, which method should you actually trust? Nobody's saying TON 618 lost its title. It didn't. The cosmic horseshoe black hole is still smaller. But it's the first serious data point measured a fundamentally different way, and it's forcing astronomers to ask a harder question. Not what's the biggest black hole, but have we ever actually measured that correctly?
While everyone argues about the mass, there's something sitting right next to TON 618 that almost nobody mentions. In 2021, the ALMA Observatory confirmed TON 618 is wrapped in a massive cloud of neutral hydrogen gas, a Lyman alpha blob. Size? Roughly 330,000 light-years across. For scale, the Milky Way is about 100,000 light-years across. This gas cloud is over 3 times wider than our entire galaxy. The quasar's radiation lights the cloud up like a flashlight through fog, except the fog spans 1/3 of a million light-years, and the flashlight is one of the most energetic objects in the observable universe. Structures like this are thought to hold raw, uncollapsed gas sitting in the space between forming galaxies. Some researchers think this exact blob has been feeding the black hole for billions of years, which might explain part of the mass debate we just covered. A black hole with a galaxy-sized fuel tank sitting next to it doesn't need to break the rules to grow fast. It just needs enough fuel and enough time. It's one of the only pieces of hard evidence tying directly into how TON 618 got this massive this early. And it barely shows up in any video on this topic. Now it does. Most videos on TON 618 end the same way. We'll never know what it looks like today. The light takes billions of years to arrive. True. Also, not the interesting part anymore. Here's the real takeaway. TON 618 isn't famous because we know exactly how massive it is. It's famous because we don't. And the size of that gap tells you something real about the edge of modern astronomy. We can detect light from 10.8 billion years in the past. We can calculate it outshines our sun by 140 trillion times. But ask the simplest possible question. How much does the thing in the middle weigh? And the honest answer spans nearly 30 billion solar masses, depending on which method you trust. That's not a failure. That's what science looks like at the edge of what we can actually observe.
Biggest black hole ever found makes a clean headline. The reality underneath it is two teams looking at the same object and landing on answers that disagree by almost a factor of 2. That gap is exactly why TON 618 keeps getting studied. Every new instrument, every lensing survey, every reanalysis is really one thing, an attempt to shrink that uncertainty a little further. So next time you see a headline call something the largest black hole ever discovered, ask the only question that actually matters. How was it measured? And has anyone ever checked? With TON 618, we already know the answer. They checked, and the two answers didn't agree.